All right, so today we are going to continue our discussion of conservation laws from last time. And um, last time we talked a little bit about basically a review of the energy and the energy in our classical or Newtonian understanding. And there are some exceptions. So let's review. The first one is in Einstein's general relativity. When when the universe is expanding, the wavelength of traveling light would increase because the space is not constant and it is dynamic. And therefore the wavelengths would change and the energy would drop because the frequency would decrease as wavelengths increase. And that means the energy is not constant. And this breaks the conservation laws. As well as when dark energy creates energy out of nowhere, which accelerates the expansion rate of the space. And so that tells us that conservation laws are no longer fundamental properties of the universe, and therefore there came a new understanding of the fundamental properties of the universe, and that comes in handy for understanding our current conservation laws. And so, yeah, let's take a look at the principle of least action. And this is how, this is the fundamental or axiomatic principle that leads to the law we will introduce later. So let's first think about Fermat's theorem. If you think about our SAT YouTube videos, we learned about the principles on which light travels. There's the law of reflection. There's a law about how light deflects. And all of these actually summarizes into how light finds when it's traveling. It will always find the path that minimizes the traveling time. So whichever way that it goes faster, it would travel that way. It seems like a paradox because it has to try a few ways until it finds the shortest time, but it is that way. And this is described in the principle of least action. And so when we generalize Fermat's theorem or this principle into all things in the universe, that's how all things in the universe operates. Basically, everything will choose the path to minimize action. And the term action is not always about like light, how we discussed, always minimize traveling time. This concept of action is very well described by this function called a Lagrangian function. And action would be the integral of this property of Lagrangian. And this function is, it contains the meaning of an object's physical state. So let's learn about Lagrangian and this action thing. So here we have I think, yeah. So we will learn about Lagrangian later. Don't worry. So we first, so let's assume like least action principle, the principle of least action. We learned about that. It's true. And when we have that principle, we have this Noether's theorem. So Noether's theorem allows us to figure out the true conserved quantities for any system, and it follows the principle of least action. And this is useful in finding symmetry, and yeah, so actually, um, I think don't worry about what these term means. I think the order is a bit of confusing here, but yeah, let's go to the next slide first. So this is Noether theorem. So what it says is if a system has a continuous symmetry, then there must be corresponding quantities whose values are conserved. So let's learn. Continuous symmetry means that some parameters in the system is unchanged as the object change in the direction of this coordinate. So think about symmetry. For this butterfly, you can flip it and it will be symmetric because when it's changing in some, you can think about it's flipping in some coordinate or some direction. It is the same. And continuous symmetry means that if it's changing in that direction, no matter the magnitude of its change, some parameters will always be the same. So if you're moving along a straight line, you're moving in the same direction, everything is the same. Or if you're rotating around a point, everything is same, is called continuous symmetry. And uh, so under Noether theorem, what is special, and basically that's what the last slide was saying, conservational laws are a special case, and Noether theorem is a better and more generalized, more fundamental description of the universe. So uh, let's think about our classical conservational laws in Noether theorem's term. So if there is time translation symmetry, if we are moving in a direction of the time coordinate, and uh, if that is symmetric, if when we move, the object experiences constant physical effects. For example, when time changes, our object would experience the same gravitational force, like a roller coaster. It would have the conservation of energy. So the conservation of energy is only true when there is time translation symmetry, or when time changes, everything stays the same. So next we have space translation symmetry that gives us conservation of momentum. And that symmetry means when we are moving in a direction, the objects experience constant physical effects. And you can think about a car that's moving on a flat road. Um, that symmetry is how, like when I said, when we are moving in a directional coordinate in an actual space. So direction is an actual space. You have um, a flat road. That means that all the force on the road is the same. And when you travel, because it's flat and straight, you don't have any you don't have any alteration in altitude. So that means your momentum will be conserved. And if you think about classical terms, if you're traveling, there's no energy loss or whatnot. So you have the same momentum, and that means when you are moving in a direction, you have conservation of momentum. And in classical terms, um, when you are calculating the conservation of momentum, you don't have to take in account of time because um, that symmetry is only about space. So yeah, that's a nice understanding of that conservation laws. And rotational symmetry is very similar to space translation symmetry. The only difference is that the object is now not moving in a line, but is rotating. So it could be satellite rotating around the Earth, And when it rotates, when it changes angle, the object experiences constant physical effects. So um, that means the conservation of angular momentum is a special case when that's only plausible when rotational symmetry is present. So now we can look at what Lagrangian means, and this is behind the mathematics of it. So it is just a function, and it includes some parameters that's concerning the object's physical effects. So for example, here we have a Lagrangian. It includes T. It actually means EK, KE. Yeah. So it's kinetic energy, and minus V. V is potential energy. And it could be various multivariable. It could be multivariable functions of many terms. The function could include a lot of parameters, but here, for example, we can have time, we can have its location. Yeah, so next slide, we are just going briefly over this. So we are not going over the calculus. We just look at how it's basically working. And this is an analysis of the conservation of momentum. So we have momentum and force. Force would be the integral of momentum, or I'm sorry, a force would be the change of momentum. It would be the time derivative of the momentum. It's basically a force is how much momentum change in a period of time. And then Lagrangian, if we take the derivative of Lagrangian here, the Lagrangian derivative of it would be 0. That means Lagrangian is constant and it would be symmetrical. And the condition that Lagrangian would be constant is that Lagrangian is Lagrangian that Lagrangian is equal to I'm sorry. The condition that is constant is that momentum and force have to be time derivative. So the first part that I said is above is the first four equations, and these equations tells us that the change of L is 0, and the fact that it is true and it is true would be another proof that is very direct. And so basically, if it's a proof that is proving itself, if we when we have this c constant equals this derivative, we can prove that it is true by taking its derivative, and we have to plug in p equals the partial derivative of L over change of Q, and so forth. We have to prove it, plug in the first two equations, and then we get it. So that is a very well, basically what I described is how the conservational laws has the condition that basically force needs to be the time derivative of momentum, and that is the precondition of the symmetry, and that is why this thing is true. So we can both see how the symmetry has work and why it's at work, the condition of it, and what angular momentum means. Yeah, so hopefully that wasn't confusing. There's always online researchers who can do a better job, but now Kahoot might be a great resource.
All right, now we're going to use a Kahoot to review some of the key concepts that we have been covering in the unit. So I'm going to go set that up. All right, so here's the Kahoot, everyone. So there's the code for the Kahoot. Please join the Kahoot. We'll give you guys a minute or two to join. All right. All right, let's begin. So which of the following here is false, is the first question. So here we have an example of the key thermodynamics vocabulary. And so if you remember from thermodynamics vocabulary, some of these options are here are correct, right? Closed system exchanges energy but not matter. Boundary will separate system from rest of universe. And adiabatic processes are one of the 5 types of processes, right? Adiabatic has no heat transfer, right? But heat is actually a path-dependent state variable, right? Work and heat are path-dependent, if you remember that term. Let's continue. Next question asks, which of the following are false as well? So this question, I think it also has like reinforcing the previous one. An adiabatic process is a process without any heat transfer, right? So actually there's a cyclic process, right? A cyclic is one of the other 5. And in cyclic process, a system will return to the original state. Then we have like isobaric process, isochoric process. Isochoric is the same volume, isobaric is same pressure, right? And we have like extensive properties, which is energy, volume, and mass. They depend on extent of the system. And then you know that work is pressure times volume. We have that key idea. Let's continue. All right, this one was like a freebie here. I guess the example in the picture is a good example. All right, yeah, so here you guys can see the mechanisms of heat transfer. You have a heat source, right, which can radiate the heat. We have convections. We were looking at Lorenz and convective rules, how it's heated at the bottom and cooled at the top. And then you have like conduction, which is direct contact heat transfer here. So you guys can see some of these ideas in mechanism of heat transfer. So read the statement carefully and decide whether it's true or false. All right, so in this statement, we should note that compression will occur when external pressure is greater than internal pressure, and expansion will occur when external pressure is less than internal pressure. So this statement did the opposite here, using a greater here instead of less than. And so this would be incorrect. Here's double points question. Remembering the first law of thermodynamics. Which of the following is not derived from first law of thermodynamics? So you'll remember, so this yellow option here, heat does not flow from colder to hotter. This is true, but this is actually derived from the second law of thermodynamics and not the first law of thermodynamics. The rest of these options are consequences of first law of thermodynamics. Hopefully you remember like the bird, this toy right here. It's from the statement that perpetual motion is impossible, right? Although it may seem like a perpetual motion machine, that does not actually exist. So these other three options follow from definition of entropy, right? It's reversible heat over temperature is the key idea in change of entropy. It can also be like, if you remember K natural log of omega, there's the Boltzmann idea regarding the molecular disorder in system, or the number of microscopic arrangements or states also follows from that. But if there's more entropy, then it's harder to do work, is how we conceptually think about it. So this is the opposite here. Let's continue. All right, so I think that this was a difficult one. So heat always flows from hotter to colder is a correct statement. And so you remember from the first law of thermodynamics question, there was this idea, which is actually from the second law of thermodynamics, which is why it was wrong for that question. This is the second law of thermodynamics question. So this statement is true. Entropy increases in processes and reactions is also true, right? You guys remember that the entropy will tend to increase is part of second law. Usually processes with no enthalpy are spontaneous. This is an idea from Gibbs free energy, actually. So this green one is a really tricky option, but you should probably review Gibbs free energy. And so this is the idea. Basically, work can be converted into heat, but this vice versa was the trick. A heat cannot be converted back into work, which is consequences regarding like efficiency, right? In second law of thermodynamics, you can't like take the heat, turn it back into work, right? Say like your hair dryer, right? And that's releasing heat. You can't take the heat and put that like back into the hair dryer, for example, right? So you can't get back the same amount of work essentially. Here's Gibbs free energy. I think this is like a multi, yeah, two of these work. So here, there's so you can see we kind of put the formula here. The Gibbs free energy is equal to change in enthalpy minus the temperature times the total entropy. You can read it from here. And it can also be described as how spontaneous a process is from perspective of the system. It basically tells us will a chemical reaction occur or not. Is what we can understand through Gibbs free energy. All right, what is chaos? You can look at this GIF of a double pendulum while deciding the answer here. We didn't get to look too much at this idea, but it's very interesting. It's very hard to replicate trajectory. Impossible, right? Because of sensitive dependence on initial condition, it's impossible to replicate the trajectory of this. So here, chaos, you can see is aperiodic, seemingly unpredictable behavior in deterministic system will be the definition of chaos. Let's continue, guys. We're kind of running out of time. Which is not part of face portraits here. There's something here that doesn't belong in one of the answer choices. So Noether's theorem and conservation laws is today's topic, and that does not involve face portraits. The rest of them involve face portraits. If you remember the mathematical example that we were trying to do, as well as the pendulum, those are face portraits. Who's the famous character that we discussed? Was understanding chaos. So he was just trying to understand the weather. Or yeah, so that would be Lorenz. Lorenz was trying to understand the weather, right? And the rest, he basically came up with ideas about chaos. He was a meteorologist, right, and trying to understand the weather. The rest of them are not as prominent in chaos. Poincaré is actually a bit prominent because he fathered up some earlier notions of chaos, right? It was what he thought about. He came up with those ideas. We'll do one more question. And then we'll call it. And which of the following cannot be modeled using Lorenz's equations? This is a very interesting one, right? Because we were looking at Lorentz equations like last time, right? And so a lot of different things can be modeled, but one of these things does not work in Lorentz equations. Conduction cannot be modeled using Lorentz equations, right? This picture is supposed to remind you of kind of like dynamos, right? There's a whole system with like a hydroelectric dam that connects to like this here. And so you can model dynamos, you can model water wheels. Remember the water wheel, the common example, famous example. And we have lasers as well using the Lorentz equations. As of now, we'll stop. And I'll include like the link to the Kahoot. I'll make that available on VClubs and in Discord, of course. So thank you so much, everyone, for playing today. Hope you guys all learned something about conservation laws and were able to review the thermodynamics.